Introduction to sets. A set is a collection of well-defined objects. Objects in a set are called elements. Sets are usually denoted with an uppercase letter, for example, capital A, and listed within braces. So we have a brace on the left side and the right side. They're also known as curly brackets, and the numbers that are between our braces are the elements of our set A. So we have -3, -2, 0, 1, and 4. When stating which elements are within a set, the Greek letter epsilon is used. So this 0 and then epsilon A is actually read as 0 is an element of, that's what the epsilon stands for, is an element of set A, or 0 is contained in the set A. When stating which elements are not within a set, the Greek letter epsilon is used with a slash mark through it, meaning it's not an element of, or it's not contained in the set. So this 2, the slash through the epsilon and then A, is read as 2 is not an element of set A, or 2 is not contained in the set A. There are 3 methods commonly used to describe or represent a set. The first form is statement form, which is a written statement that describes the set of numbers. For example, a set B is defined as the first 5 counting numbers greater than 0. We could also write the set in tabular form, which is the list of numbers contained within a set. So that was similar to what we saw on the last slide with our set A. They are written between our braces and separated by commas. So here's another example. Our set B, which is the first 5 counting numbers greater than 0, are within our braces the numbers 1, 2, 3, 4, and 5. We can also write it as set builder form, which is a description of a set that uses a rule or an algebraic formula to describe the set. So this same set of 1, 2, 3, 4, 5 can be written as B is an x value contained in the natural numbers such that x is between 1 and 5 and includes both endpoints. We also have what's known as an empty set, and that is a set that contains no elements. It can be denoted by the curly braces with nothing in between, or the Greek letter phi. The cardinal number, or lowercase n, of a set is the number of elements that a set contains. So if we had the set A to be -3, -2, 0, 1, and 4, and set B is this empty set, the number of items in set A, or the cardinal number of A, is 5, because we have 5 elements in set A, and the cardinal number for set B, or the number of elements in B, is 0, because it's empty. 2 sets are considered equal if they have exactly the same number of members. For example, if we had a set C, that was the digits 0, 1, 2, 3, and 4, and a set D, the set whose numbers are the first 5 whole numbers, we would end up listing them, if we wanted to, in braces for set D, and we would get the same exact elements, 0, 1, 2, 3, and 4. Because whole numbers begin at 0 and then continue to increase by 1. Here's another example. We have our set A, which is -3, -2, 0, 1, and 4, and set B is our empty set. Here, A is not equal to B because they do not have the same exact elements across both sets. Let's try an example. We're given a set F to be the numbers 1, 2, 3, 4, 5, and 6, and set G is an empty set. Determine whether each statement below is true or false. So our first problem that we have is that the number 5 is contained in the set F. If we look at F, it does indeed contain the number 5, so this is a true statement. Now let's look at our second statement. 2 is not an element of F. Well, that's false because 2 is right here. and it is contained in the set F. Now let's look at our third one. Set G is an empty set. That is true. It has no elements contained in it, so it's empty. Now let's look at the next one. 1 is an element of G. Well, G is the empty set, so this is false. Now let's look at the next problem. The number of elements in set F is equal to 6. 1, 2, 3, 4, 5, 6. There are exactly 6 elements in F, so this is a true statement. And now our last problem, set F is not equal to set G. That is also a true statement. Set F has the natural numbers 1 through 6, and set G is empty. They are not equivalent or equal to one another. And here again are the solutions to this set of examples that we worked through, and the solutions circled match the solutions that we found. Now let's try another example. Here we have set H, which contains the numbers 2, 4, 6, 8, and 10. And set I is an empty set. Determine whether each statement below is true or false. Our first one that we have is that 8 is contained in our set H. 8 is definitely an element of H, so that is a true statement. Now let's look at our second one. 5 is not an element of set H. Well, that's also true because these are all even numbers. So this is a true statement because it says 5 is not an element of H. Now let's look at our third one. 1 is an element of I. Well, I is an empty set, so this is a false statement. Now let's look at our next one. I is equal to a set that has empty braces or is an empty set. That is a true statement because it says the same thing up here. It's an empty set with the Greek letter phi. This is the other notation for having an empty set. Now let's look at our next problem. The number of elements in set H is equal to 6. Well, if we count these, 1, 2, 3, 4, 5, those aren't equal. There are only 5 elements in set H, not 6 of them. And now the last statement, set H is equal to set I. This is a false statement because set H has 5 elements, set I has 0 elements. It's an empty set. Here we see the solutions to the example problem that we just solved, and the solutions circled or shown on the slide match the solutions that we found while working through it.